Hi, my name is Jim Noggle. I'm a math teacher from Pendleton Heights High School in Pendleton, Indiana. I'm very honored to be selected by the teaching company to present this series of geometry lectures for you. I represent not only my family and my colleagues back home, but also I represent the geometry teachers across the United States and even around the world. The geometry facts that I want to present to you are not things that I've made up myself. They are facts that have been with us for many, many years. We will be taking some of these facts one at a time and building a solid foundation. We will take nothing for granted, so it'll be easier for you to understand. Just like building a house, we cannot start with the walls or the roof when we build a house. We have to start, at ground level. We've got to start with the foundation. So that's what we're going to try to do here in the beginning. We will start out with the basic ideas of helping you try to visualize the relationships of points and lines and planes in space and how these things work together and interact with each other and create angles and then triangles and other polygons and on into the circles. And then we'll do a series of constructions and end up from the two-dimensional concepts and expand that on into the three-dimensional concepts in the last 2 or 3 lectures. So, again, just relax and try to comprehend the best you can. We'll try to present it in a very logical order and build upon our basic facts and go from there. In fact, I'd like to nickname this course How to Succeed in Geometry Without Really Crying. First of all, let's take a look at our basic idea. We have to start with some undefined terms to get started in geometry. We talk about points and lines and planes and how they react to one another in space. So we begin to visualize some of these things all coming together. First of all, a point is actually represented here by a dot. Now, a point technically has no dimension. And it really is not really a defined term. It's just an intuitive idea. We say, well, I can see that dot right there. It's got dimension. I can measure it. It's about a ½ an inch in diameter, or ½ an inch wide, ½ an inch tall. But that is just a dot. That is not a point. That dot right there represents, officially, the invisible point. So technically, a point has 0 dimension. We have 0 dimension with a point. Now, we can have several points like this out here at random and drawn around like this. And beginning with these points now, we will expand on into lines, and then planes, and then space. And with this, we will learn about these things through postulates and theorems. Now, let me explain these, first of all. 2 very, very important words in this series of lectures. We have over 200 some postulates and theorems altogether. And with all these things presented and put together like puzzle pieces, we can really solve a lot of things and really create a lot of unending ideas in geometry. First of all, let's understand what these terms mean. Postulates are also sometimes called axioms, and that is a statement. A postulate is a statement that we can accept as being true without any kind of a proof. Okay? It's just pretty much a common-sensible idea that we can accept, and we don't need to argue or to prove it. So that's what a postulate is, a common-sensible statement that we can accept as being true without any kind of proof. A theorem, by contrast, is a little bolder statement, and it must be or can be proven before we can accept it as being true. Now, with these 2 things together, we can evolve and derive other theorems and ideas together, and we can prove them by previously learned postulates and theorems. So it just kind of snowballs. We start with the foundation of the beginning theorems, and we just kind of build upon them, and we get a bigger and bigger foundation underneath us. So try to stop and comprehend these things as we go along. And remember, you have the luxury of stopping the tape and rewinding to pick up something that you didn't understand the first time. So again, a postulate is a statement we can accept as being true without any kind of a proof, and a theorem is something that we must prove before we can accept it as being true, before we can go on with it. Another nickname for theorem is a corollary, plural corollaries. Now, some textbooks will have these as different things, but they're really kind of very similar. Other textbooks will not even recognize corollaries. They'll just present them all as theorems. They're very, very closely related to one another. In fact, I've seen some books where a theorem in one book was a corollary from another theorem in another book. So they're very closely related, and so rather than getting bogged down into, which is this a corollary or is this a theorem, I'm just going to present this from the standpoint that they're all going to be basically theorems, all right? So basically corollary is a theorem, really, that's a spin-off from another theorem. A corollary really evolves directly from a first stated theorem. But again, for all practical purposes, I'm going to group them all together as just theorems. So we'll have postulates and then theorems together. Okay, let's take a look at our very first postulate. This gets everything started with the idea of points, lines, and planes in space. Postulate 1-1, our very first postulate idea. Given any 2 points, there is a unique distance between them. Okay, that's pretty much accepted as true without any kind of proof. That's why it's a postulate. There's a unique distance between them. Whatever that distance is across there, whether it be 9 inches or 10 inches, there's no other line segment that can be that length between A and B. We will not recognize something like this or something like this. That doesn't count. So again, given any 2 points, there's a unique distance between them. Now, let's take a point in this drawing back here, and let's slide it along. Remember, a point has 0 dimension. A point technically is invisible. We represent a point by these dots. So if we take a point and slide it along a path, let's take this point O and slide it right here through point N. Both ways. And we'll call that line L. Now we can name a line by one of 2 ways. We can name a line by a single letter like L, like I did here, or we can name it by using the 2 points that it may pass through. So we can call it line ON or line NO. All of those are different ways to name the very same line. Okay, now lines are one-dimensional. We take this invisible point with 0 dimension and we move it along a certain direction, and then it becomes one-dimensional. Now we can connect other points, and let's say we draw a line through P and O like this. We can call it another name. Let's call that line K, and another line through T and I like this, and we'll give that another name. We'll call that line M, and on we go. We can draw a line down through here, P, I, and N like this, and we'll call that line C. Okay? Now, again, we can call these by the same similar names here. K, line K could be called line PO or line OP. Line M over here can be called line TI or line IT. Now, notice the little hats that I'm putting on top of these letters. I put little arrowheads on each end. That indicates that the line, technically, goes on out each way infinitely far. A line never stops. Technically, a line never stops. That's why the little arrows you see are on the ends of them. And that one too. Then, let's see. Line C could be named line PI using these 2 points, or it could be called line IN since it passes through those 2 points, or it could be called line PN like this. And of course also, these 2 can be reversed. Usually we write them alphabetically, but they don't have to be at all. So anyway, these are different ways to name the very same line. Now, points can be collinear if they lie on the very same line. So, of course, 2 points would always be collinear, but line C would have, as we have in here, 3 collinear points. They're all 3 along the same straight line. P, I, and N are collinear. Collinear. Let's write that term up here. C-O-L-L-I-N-E-A-R. Points that would be non-collinear would be 3 or more points that do not lie on the same straight line. Like T, O, and N, for example. T, O, and N are called non-collinear points. Okay? Another example of non-collinear points would be points O, I, and P. O, I, and P are also non-collinear points. Now, lines can be, as I said, one dimension, but their relationships among each other, among other lines, can be one of three. Lines may be parallel. That means they never intersect. And when they are parallel, we usually put a little pair of arrows like that on there. That indicates that they're parallel. That's just a mathematical symbol to show that they are, in fact, parallel. So the lines can be parallel, or they can be intersecting, or in space, we'll call this line D and line F. Lines D and F intersect. Here they intersect obliquely. That means in this plane they intersect at some other angle other than being what's called perpendicular. So there's a special case of intersection. And when two lines intersect in a perpendicular manner like this, we'll call this line G and line H. We usually put a little symbol right there at the intersection point. And that indicates that since they're perpendicular, then that forms the right angle right in there. And we'll talk more about that and how that evolves into right triangles and other things later in the series. But again, two lines can be parallel to each other or intersect each other obliquely like this, or they may intersect in perpendicular form like this. The third form that lines could be is called skew lines. S-K-E-W. That's where one line would be going this way, and if you can visualize a three-dimensional drawing, here comes another line out towards us this way. Let me demonstrate here. Here's the three cases for two lines. They may be parallel to each other like this. They may be intersecting like this. Or they could be perpendicular, that's also intersecting. Or they can be skew lines, S-K-E-W, like this. That means they never intersect and they're not parallel either. A classic example of skew lines would be like roads and overpasses. One goes under the other or over the other. And in some big cities, I've seen as many as 3 and 4 highways going over each other, like skew lines. Parallel lines are everywhere in our world. Parallel lines like along the side of the road, alongside the highway, building edges, the edges of framework, doors, windows. Parallel lines exist everywhere. Siding on houses, whether it be vertical or horizontal siding, framing, everything. There's a lot of parallel lines in the everyday world. So again, the three positions for two lines in space would be, they could be parallel, intersecting, two cases, or skew lines, where they never intersect. Now, let's talk about planes and how they relate to one another. Planes can be named a couple different ways as well. Now, this is like a flat plane area coming out towards us, if you can visualize this three-dimensional drawing on a two-dimensional board. A plane is like a line in that it's infinite. It goes on and on forever, technically. So these edges of the plane would keep on going forever on out into space. Now, we have to chop it off someplace so we can see the region we want to deal with, but technically, the plane itself is infinite. Now, we can call this plane by one single letter, like plane M, or if we know 3 points that are in the plane, then we can call the plane ABC. So again, we can call this plane plane M if we just tuck away a big capital letter down in the corner like this, out of the way. Or again, if we know 3 points or more points in the plane, then we can call that plane, in this case, ABC. Now, planes can be related to points if the point is on the plane, like A, B, C, D, and E, and F, and so forth. If those points are on the plane, then the plane is said to contain the points. If the point is down below, like X, let's say it's down below the plane, or point Y back down over there, or point Z up here above the plane, then those are said to be non-coplanar points with the plane M. They lie above or below the plane. Now, with lines, the plane can have a line that would be contained all in the plane, like line AC. So that line could be contained in the plane, or a line could intersect the plane like this. We'll put the dotted line in here, so technically that's below the plane where we cannot see it in this drawing. So the line could intersect the plane in a point, or in that case, too, it could intersect at a right angle, perpendicularly to the plane. Or the line could be parallel to the plane up here, where it never intersects the plane. So that's a relationship that could exist with a plane and a line. The line can be in the plane, the line can intersect the plane, or a line can be parallel to the plane. Now, let's talk about the next dimension, and that is space. Two planes can be parallel to each other in space. If we have another plane down here below this plane M, let's call it plane, doesn't matter, plane R, then again, that's extended all ways infinitely far, like this. And visualize again, if you will, these two planes being parallel. There's only two relationships that can exist for planes, and that is, number one, they can be parallel, or they will eventually intersect. There's no such thing as skew planes. If you extended them far enough, they would eventually intersect. So again, if you have two parallel planes like this, then they would never intersect, just like the ceiling and the floor, or the side walls are parallel to each other. Or if you extended them far enough, if they were not parallel, then they would eventually intersect. And if the two planes do intersect, then we would have a plane crash. No. If two planes intersect, then you'd have a line right here. That's another possibility. Two planes would intersect in this straight line. Okay? Now let's talk about space again a little bit more. Space technically is the set of all points. It is all-inclusive. It includes all points and lines and planes because we live in a three-dimensional world, so we can comprehend everything three-dimensional and less. We can understand one-dimensional things and zero-dimension ideas like points, and then one-dimension, two-dimension, and then our three-dimensional ideas. We can all understand anything our dimension or less. We don't understand what we mean when we say the fourth dimension. There's a lot of science fiction about that. Maybe the fourth dimension is time or something else. And, of course, we know the fifth dimension was a rock group back in the 60s and 70s. But the space contains all points. Space contains all points. Let's look at some other points along a particular line, ways to name them, and then some subsets of lines that evolve as a result. Let me take a line with 4 collinear points. 4 collinear points. Let's call them A, B, C, and D. Those are 4 collinear points. We can name this line by using any 2 of those points. Well, first of all, we said we could call it by one single letter at the end like this, out here at the end of our drawing, and call it line L. But in terms of the letters, we can call that line AB, or line AC, or line AD, or line BC, or line BD, or line CD. We can use any 2 of those 4 collinear points and name that line. They're all names of the very same line, since the points are all collinear. Also, it's true that this could be equal to the same as line BA, or line CA. We can turn them around, just like this, line CA, or line DA, and so forth. You get the idea. Now, usually, not always, but usually we write them in alphabetical order just for consistency's sake, but there's no magic as to why we have to do them like that. Now, let's look at some subsets of lines. There is the whole line itself going out each way infinitely far. What are some subsets of lines? Well, first of all, points themselves could be a subset of the line. The line itself, of course, the whole line, which is a whole set of points, would be a subset. But other subsets would include rays. Ray AB would be written like this. AB with that little arrow above it. Now, this indicates, if you look at this, there's no arrowhead above A. So that would indicate that it starts here at A and goes on out one way through B. The arrowhead tells us which way to go. But also, the arrowhead means it goes on out that way forever, so if it goes on out through B, it must go on out through C. So that could also be named ray AC. And if it goes on out through B and C, it keeps on going because of the arrowhead. We could also name that ray AD. So those are all names for the very same ray. You notice they all have the same starting point, point A. Sometimes that's referred to as the end point, but I prefer it to be thought of as the starting point. So starting point or end point of the ray. The other part of the ray goes on forever. So this is one subset of a line. Now, if a ray starts from the same point and goes in different directions along a line, let me use a different drawing for that since I got that one kind of botched up already with different markings. If we have another line here, let's just use 3 points here, points A, B, and C. If we start here at point B and go in this direction, and we have another ray starting at point B going in that direction, those are said to be opposite rays. So, again, ray BA and ray BC are opposite rays. Opposite rays. They have the same starting point, but they go in opposite directions along the same line. Here's a question for you. Would ray BA be the same thing then as ray AB? Well, based upon just what I explained here about rays, notice the starting point. This one starts at B and goes out through A. We'll mark that in the yellow. So starting here at B, it goes back this way. And the other one, we'll mark in orange, starts at A and goes on out through B. So that would be here, starting at A and going on out through B that way, along the same line. So you can see they are not the same rays. They're not even opposite rays because they don't even start at the same place. They're just two different rays. So with rays, my point is you cannot change the lettering around. You can with lines because the line goes out each way, infinitely far. But you cannot turn the letters around when it comes to rays. If we have segments along this line, let's draw that same line again. A, B, and C, collinear points. We call this line segment AB. Line segment AB. This is another subset of a whole line. A segment AB is written like this. It starts at one point and ends at another point. So its hat is just a straight line across there, a straight line segment with no arrowheads on either end. So line segment AB would start here and go out to B. It starts and stops. No continuation on forever. That's a line segment, AB. We also have line segment BC. And that would be, of course, from here on to there. And we have then, of course, line segment AC. If we mean starting here and going up to there. Or starting C and going back to A. Wouldn't matter. So line segment BC, for example, is the same name as line segment CB. Just like that could be called line segment BA, this could be called line segment CA. Okay, so they could be turned around because the same thing happens at each end. If we have, in a same drawing, in the same problem, if we have more than one pair of congruent segments, let's say this line segment AB and BC are congruent. There's a new term. The word congruent means equal in measure and size and shape. We can have congruent line segments. We can have congruent angles. We'll talk about that in the next lesson. We can have congruent triangles or congruent polygons, congruent circles even. But it is not proper to say congruent numbers. So again, congruent means equal in not only a numerical value, length, but also in all geometric shape and size. So congruent is all-inclusive word, meaning it's the same geometric shape, size, and everything. So in a drawing, if you had other lines that were maybe the same length, like we'll call this line segment DE, and that was equal in measure to line segment XY down here. then we can mark those with two little marks. So to distinguish them separately from these marks here. They might be a different length, you see. Or if we had another line out here in the same drawing and a line here that were the same length to each other, then we would mark them by three little hash marks like this. So when you have two, or I should say more than two pairs of line segments that are congruent in the same drawing, use little marks like this to pair them up. You can see which ones belong with which ones. Now, if AB, line segment AB, if line segment AB is the same measure or is congruent to line segment BC, then B is the midpoint. B is the midpoint. Let's take another look at another idea. Any segment has exactly one midpoint. That's pretty much commonsensible, and we'll put it right there. Call that point M. There's only one point along a certain line segment that can be its midpoint. That develops a theorem, our first theorem. Theorem 1-1 evolves as a result of that postulate. The midpoint theorem says if M is the midpoint of a segment AB, then here's what happens. 2 times this segment AM equals the original segment AB. It just shows a relationship of the whole thing to its one part. And the same thing true on the other side. 2 times the measure of MB equals the whole original segment AB. Or, multiplying both sides here by 1/2, you would get this version here. AM is 1/2 of the entire segment AB. So, there we have the midpoint theorem, our very first one. Now, a segment can be bisected by several different things. A segment can be bisected not only by a point, but it can also be bisected by a line. Let's take a line HM. And let's say there's its midpoint. We'll call it A for now. Okay, so this line segment HM can be bisected by this point. That would be its midpoint. It could also be bisected by a line. If we drew a line through it, call that line RW. That would also bisect a line segment. Another segment could bisect it. If we had just a line segment XY, that could bisect it if it went through the midpoint. A ray could bisect it, starting here, let's say at A and going out one way. That ray could bisect the line segment HM. And even a plane. If we had a plane slicing through here, slicing right through the middle of line segment HM, that would also bisect a line segment. So any way you slice that ham, you've got a midpoint right there at A. Okay, we need to establish a system of linear measurement here to get started, and the ruler postulate is the way to get started with that. And again, it is a postulate, which means we can accept it as being true. The ruler postulate says any 2 distinct points on the line can be assigned the coordinates 0 and 1. That's just a way to get started, so we have an established scale. Then there's a 1-to-1 correspondence between all the real numbers and all the points on the line. Remember, all sets of real numbers, the set of real numbers are all infinite, and the set of points would be infinite. The distance between 2 distinct points on the line is the absolute value of the difference of the coordinates. The absolute value of the difference of the coordinates. So, for example, if we put these points along a scaled line, like the number line, let's say we have this number line, and we've got a point back here at -1, -2, and a point over here at +3. Okay, part 3 of the ruler postulate says that the distance between these 2 points is the absolute value of the difference of their coordinates. The coordinate of A is -2, the coordinate of B is 3. The absolute value of their difference, it says, would be written like that. Now, inside there, we would get a -5, but it's the absolute value of -5. Distance always has to be positive. So that's why we have to say absolute value. And that way, it doesn't matter which number do I put down first. Relax. It doesn't matter. You get the same answer anyway. Look at this. If I put down the B number first, 3 minus the other coordinate, 3 minus a -2, that's the absolute value of a +5. Still the same answer. So absolute values allows placements there in any order. You don't have to worry about which one you put down first. And last of all in this lesson, the segment addition postulate. If C is between 2 points A and B, then by common sense, this measure of AC plus this measure of CB is officially equal to the same measure as the entire segment. That is what's called the segment addition postulate. That will be our first one of this series. There's also what's called an angle addition postulate we'll talk about in our next lesson. And it expands on from there. Area addition postulate when we get into areas. In our next lesson, we're going to talk about angles and angle measurements. And we're going to see how these are related to points and lines and planes as we begin our foundational development to get on into triangles and more two-dimensional figures.